Okay, so this is the last part of Module 3, which is a discussion of the BJT transistor as an amplifier. In this particular session, I'm going to introduce the BJT small signal model. Before doing that, I'd like to give you a short primer on two-port networks. What is a two-port network? Let's say I have a network here, N, and this can be a very complicated network. This can consist of a number of elements inside this particular network. Okay. If this network can be characterized with respect to two sets of terminals, or what we call ports, with each port having a voltage and a current variable. So, for example, you have this port, then you have both a voltage and the current associated with this port, and then you also have this port, port 2, with a voltage and a current associated with it. Typically, one port will be the input and the other port will be the output. So this might be your input port and this might be your output port. Okay, the concept of two-port networks is applicable to networks containing linear elements with no independent sources. So this must contain only linear elements. So your linear elements are either your linear passive elements or your linear dependent sources. You cannot have nonlinear elements and you cannot have independent sources or nonlinear sources. Okay. What are your linear passive elements? Can somebody tell me? Ano yung mga linear passive elements natin? Anyone? No one? Okay. Yeah, a resistor is a linear passive element. Is that the only linear passive element? No? Your resistor, your capacitor, and your inductor, those are all linear elements. That's why you can apply linear circuit analysis techniques when analyzing these circuits. That's what you did in EEE 1, 2, 3. Okay. Okay. Now, the thesis is this, no? The parameters of a two-port network completely describe its behavior with respect to the input and output variables. In other words, okay, if all I'm interested in is the behavior with respect to port 1 and port 2, I can represent network N by a set of parameters, and I don't have to know what exactly is inside network N. So this might be a very complicated network, but I will be able to represent it with a small set of parameters, and that will completely describe its behavior. And in doing so, this allows large systems to be broken down into building blocks, where each building block needs only to be represented by its two-port parameters. So that is our motivation here. If you have a very complicated system, but you're only dealing with two ports, okay, then we try to simplify the inside of that system with a set of parameters. And that will simplify the analysis of the system, or the analysis of the bigger system that this system is part of. Are there any questions with regard to this? Any questions? Again, no? Important. No? You can only apply two-port network techniques if this network N contains only linear elements and does not contain any independent sources. In other words, hindi pwedeng magkaroon ng voltage source or current source dito sa loob ng N. Pwedeng magkaroon ng dependent sources. You can have voltage-controlled sources or current-controlled sources, but no independent sources. Okay, now the two-port network parameters depends on what are considered the independent and dependent variables. No? So, for example, if the dependent variables are I1 and I2, okay, or rather, no, the independent variables are I1 and I2, and the dependent variables are V1 and V2, we say the network can be characterized by its open circuit Z parameters. Let me expound on that further. No? So your dependent variables are V1 and V2. Therefore, we express each dependent variable as a function of your independent variables. So V1 will be a function of I1 and I2, and then V2 will be a function of also I1 and I2. This is function 1, this is function 2. So these are your dependent variables. And then these are your independent variables. Okay, the actual equations that are used to model the system are as follows. No? You have V1 is equal to Z11 I1 plus Z12 I2, and V2 is equal to Z21 I1 plus Z22 I2. Okay. And your Z XY, no? These Z's, these are called your open circuit impedance parameters. Okay. Now, for example, no, why first of all, why did they call them the open circuit impedance and parameters? Let's take an example. No? Let's say we want to determine Z11. Okay. To determine Z11, okay, what will I do? So this is my two-port network. Okay. This is I1, I2, V1, and V2. What will I do? Okay, to determine Z11, what I'm going to do is I'm going to put here a test voltage. Put here a test voltage. Okay. Now this is going to remind you of 1, 2, 3, right? When you want to determine certain parameters of a circuit in 1, 2, 3, there are times when you have to apply a test voltage and then determine your corresponding current. So we put here a test voltage. Okay? And then we leave port 2 open circuited. Okay, if we leave port 2 open circuited, then I2 will be equal to 0. No? Dahil open circuit to, then I2 will be equal to 0. And then we determine I1. Okay? And J11 will just be equal to V1 over I1. No? We say this is evaluated at I2 equal to 0. No? Because note that if I2 is equal to 0, this term will be equal to 0. And therefore, J11 is just V1 divided by I1. So this is your open circuit port 2. This is your open circuit port 2. So that's a process in which you determine your Z parameters. And note, Z will always be a voltage divided by a current. That's why it's an impedance. Okay. So your Z XY, this is a voltage over current, and therefore this will be in ohms. It is an impedance. Now, what will my model look like? So these are my equations. These are my equations. What will my model look like? The actual model will look something like this. Note that these are actually KVL. These look like KVL equations. Look like KVL equations, right? Because you have a voltage here, and then Z11. This is an impedance multiplied by a current. So this is a voltage, and then Z12 is an impedance multiplied also by a current. So this is also a voltage. So you have V1 expressed as the sum of two voltages. So if I try to draw the model there, let's say this is my port 1, this is my V1. V1 is the sum of two voltages. So the first voltage is Z11 I1. So this is I1. So this impedance must be Z11. Now the second voltage is Z12 I2. Okay. Now I2 is a current in another branch, and therefore this must be a voltage controlled current source because I2 is a current in another branch. Therefore this must be a voltage controlled voltage source. Okay, so this is a voltage controlled voltage source, and the value of that is Z12 I2. And then you have something similar at port 2. At port 2, okay, if you start with V2, okay, you have a current here entering, which is I2. This must be Z22 because V2 will be equal to I2 Z22. And then here you have another current controlled voltage source. This is a current controlled voltage source. This is now equal to Z21 I1. And because your circuit has a common reference, V1 and V2 would have a common reference, then we must connect these two together. Right? And if you try to write out the KVL equations for both this left side and this right side, you're going to get this and this correspondingly. So that's how you can model a complicated circuit N, okay, using Z parameters, using what we call Z parameters. Okay. So depending on what are considered the independent and dependent variables. So in this particular example, my independent variables are my voltage, my currents, and my dependent variables are my voltages. So my parameters are called my impedance parameters or Z parameters. No? So madaming combinations yan of independent and dependent variables. So the other common two-port network parameters are you have Y parameters. So Y is the reciprocal of Z. So you can guess now that your independent variables are your voltages and your dependent variables are going to be your currents. Okay. Now you have your H parameters, you call these your hybrid parameters. And the reason why they're called H parameters is because the parameters describing the circuit, ito mga parameters na ganito describing the circuit, okay, are not of a single unit. Some are resistances, some are Siemens, and some are just gains. Yun yung hybrid parameter. And then you also have your ABCD parameter, which is often used in EE, in power systems engineering or electrical engineering. Okay, so this is not a course on two-port networks. I just wanted to give you a primer on two-port networks because from this point onward, you're going to be dealing with two-point networks as applied to transistor circuits. Yun ang magiging rest of the course. Two-port networks applied to transistor circuits. Okay, now what I want to do is I want to model the transistor as a two-port network. No? Yung transistor ko, gusto kong i-model as a two-port network. In other words, example, no? Let's say my common emitter transistor. So this is my common emitter transistor, where my emitter is my reference. And this is just the transistor. This is the transistor by itself. Walang ibang nakakabit sa transistor, nagsosolo lang yung transistor. Okay. I have here an IB, that is my input-based current. I have here VBE, okay, that is my input based to emitter voltage. And then I have here a collector current, IC, and I have here also VCE. That's my output collector to emitter voltage. So what I want to do, is it possible for me to model this transistor as this? Okay, as a two-port network. And if I do so, ano yung magiging laman nitong two-port network? Okay, we said that you can only apply the principles of a two-port network if your elements are linear elements. No? If the model consists of linear elements. And therefore, the transistor must be linearized. Your transistor by itself is not a linear element. Why? Because the equations that describe the relationship between your voltages and your currents are actually exponential. They are governed by Shockley's equation. An exponential relationship is not a linear relationship. And so by itself, your transistor is not a linear element. So if we want to do this, if we want this to be modeled into a two-port network, one of the first things we have to do is the transistor must be linearized. Now, can we do that? Yes, we can linearize a transistor if the variation in the input is very small. And usually that is the case. Usually that is the case. Again, we can linearize the transistor if the variation at the input is very small, and usually that is the case. In the previous examples that I presented of the transistors and amplifier, you had very large gains. You had gains that went up to the hundreds. Therefore, for example, no, for an sabihin na lang natin, no, for a 1 volt output swing, if your gain is 100, okay, that means your input varies by only 10 millivolts. Kung yung output natin is 1 volt, gain is 100, then my input varies by only 10 millivolts. So that 10 millivolts qualifies as a small variation, as the variation in the input being very small. In which case, we are now dealing with a small signal model. Our transistor, our two-port transistor model becomes a small signal model. And that's why, if you notice my subscripts here, instead of using the capital letter, I now use the small letter. Okay, from this point onward, you're going to have to be very conscious of subscripts. Because when your subscript is a small letter, that means you're only dealing with the time-varying component of your signal. When your subscript is a capital letter, then you're dealing with the total signal. Okay. Now, because this becomes linear, magagamit ngayon ninyo lahat ng techniques na pinag-aralan nyo sa EEE 123 for linear circuit analysis. Just imagine a complex transistor circuit with many transistors, and try to analyze that circuit with the large signal model, that is with the exponential model of each of the transistors. Okay. You're going to have to go through a lot of iteration. It's only a computer probably that will be able to solve that type of problem, because you're going to have to go through a lot of iteration, because there are no closed form solutions for a system of equations where the equations are exponential in nature. Walang closed form nun. Nakakapaggawa lang nun is a computer. And in fact, that's what actually your simulators do. But if you linearize your transistor, then you can now have closed form solutions to your equations, just like the way you solve the problems in EEE 123. Particularly, since we're going to be dealing with time varying quantities, ang papasok dito ngayon are the techniques you learned in AC circuit analysis. Okay. Now, what we're going to do is we will assume what we call a unilateral model. Okay. And this is for simplification. In a unilateral model, my input will affect my output. No? But my output will not affect my input. Note that this is not always true. In fact, later on in the course, you might encounter problems where the output affects the input. That happens when your circuit has what we call feedback. And actually, maglagay ka lang ng emitter resistor sa transistor, that's already feedback. Okay, so the unilateral model is not always valid. You're going to deal with non-unilateral circuits when you take up circuits with feedback in a future course. In the meantime, we will assume a unilateral model, and actually the error due to this assumption will not be substantial. Okay, what are our independent variables? Our independent variables are going to be our input and output voltage. So our voltages are independent variables. And then my dependent variables are going to be my input and output currents. Okay. So as I mentioned, the independent variables are input and output voltages. The dependent variables are input and output currents. Now remember, we said that this is a unilateral model. In a unilateral model, the output, well, you're going to have this, no? So these are my independent variables. No, this is independent. This is independent, and then these are my dependent. No, dependent. Baliktad. Sorry, I did it again. Okay, so this is my dependent. These are dependent. And then these are my independent. No? Independent. Right? So actually this is one function and this is another function. They are not the same function. Okay, again, I said, no, we're applying a unilateral model, and we said in a unilateral model, the output does not affect the input. So actually, ito, mawawala yan. In other words, my I's of I will only be a function of my V's of I. On the other hand, my I's of O will be a function of both V's of I and V's of O. So that is how we're going to treat our transistor as a two-port network. Again, remember, we're talking about just the transistor. We're not talking about anything connected to the transistor. Okay. Are there any questions so far? Are there any questions? If I'm going too fast, please tell me to step on the brakes a little bit. Okay, pa? Okay, good. Okay, so let's try to determine the NPN common emitter small signal model. Okay, how many of you have already listened to the recorded lecture of Dr. De Leon? Don't be ashamed if you haven't. I just want to know. Raise your hand if you have. Okay, so some of you already have. Okay, well, not many of you, no, but some of you already have. Okay, in the recorded lecture of Professor De Leon test, no? She derives, or she linearizes, that's a more appropriate term, no? She linearizes the transistor using a mathematical method known as Taylor series expansion. I don't know whether that intimidates you. You determine the linearized version of your transistor using Taylor series expansion. I'm not going to do it that way. No, I want you to take a look at that lecture because it's a very good lecture. It explains quite adequately how you linearize using Taylor series expansion. I'm going to present it to you in a little bit more intuitive fashion. No? It's not as mathematically robust as what Professor De Leon did, but at least it gives you intuitively, it gives you an idea why the model is valid. Okay. So I want to create a small signal model for this particular transistor. So my inputs are VBE and IB, and my output is going to be VCE and IC. And if you recall, my independent variables are going to be my sinabi natin dito, no? My independent variables are going to be my input and output voltage, and my dependent variables are going to be my input and output currents. But in this particular case, the input current will only depend on the input voltage, because we said in the unilateral model, the output does not affect the input, and therefore the effect of V sub O can be neglected. Okay, so this is what I'm going to model. And ang magiging starting point ko is the large signal model. Okay, so here I still put here V capital B capital E. No, so I'm still assuming that these are large signal quantities that are connected to my transistor. This is my large signal model. Okay, so note that I sub C, my large signal collector current, is a function of my input, VBE, and my output, VCE. Okay, so we're already close to this, no? The output being a function of okay, this is my output current, IO here, which is IC, and then this is my input VBE, and my output is VCE, no? Based on this. So I sub C is a function of both the input and the output voltages. Okay, if I try to plot this, okay, the plot of this is also called your output characteristics, no? So the output characteristics, this is called your transfer characteristics, no? Your transfer characteristics is a plot of your output versus your input. Okay? Before we showed the transfer characteristics as a plot of the output voltage versus the input voltage. But in this particular case, what we're plotting is the output current versus the input voltage. Okay. If I plot this, I neglect for the meantime early effect. So wag muna natin i-consider to. Okay. So let's just consider this first to be let's consider this first to be negligible. Okay. This is going to be what my plot looks like, which is the diode curve. No, it looks like the diode curve, except that you have a different instead of reverse saturation current, we're talking about your scale current. No? So this is how IC will look like with respect to VBE. Again, take note, capital letters yung subscripts ko. And my transistor will be operating at a certain operating point or Q point. Now that Q point is going to be established by my DC circuit. So hindi pinapakita yan dito. Remember, we're going to divide the analysis into a DC analysis, which is the biasing, and AC analysis, which is the amplifier circuit per se. So we're only going to be talking about the amplifier circuit or the small signal model. However, it's important that you know your bias point, because everything is going to depend on, a lot of things are going to depend on the bias point. No? So our bias point occurs at VBE equal to VBEQ. So that's our quiescent base to emitter voltage. And we will have a quiescent collector current. That's ICQ. For small input changes, the slope of the transfer characteristic curve. So I mentioned this is also a transfer characteristic curve because our IC is an output, our VBE is an input. The slope of the transfer characteristic curve in the vicinity of the Q point can be considered constant. This is for small input changes. And this is how I'd like to show that. Okay. Let me blow this up a bit. Okay, so this is my Q point. Okay, if I have a change in VBE, so let's say this is my change in VBE. So around the Q point, I have positive and negative incursions of my input signal that will cause my VBE to change. My output will swing from this point to this point. So this is going to be my output swing. This is going to be my output swing. Okay, if instead of the black line, I use the blue line to characterize how much my output will change with respect to my input, they are going to be approximately equal. Because for very, very small changes in VBE, my black line and my blue line are almost the same. Okay. Again, for small input changes, the slope of the transfer characteristic curve in the vicinity of the Q point can be considered constant. That is just saying that my black line and my blue line can be considered the same, where my blue line has a slope equal to m. Okay, so again, what will happen if I have a change in VBE? So note now the subscripts. This is now V small b small e because it is only the time varying quantity. So let's say V small b small e is a positive change or a positive increase in VBE. Okay. That will create a positive increase in IC. So my output will swing from here up there, from here up there. That is the resulting change in IC, I small letter c, with respect to a change in VBE, V small b small e. If I make VBE approach 0, the slope m is just going to be the limit as VBE approaches 0 of the change in IC divided by the change in VBE. My change in IC is IC at this point, IC at this point. The IC at this point is this, IC at VBEQ plus VBE minus IC at this point, which is ICQ. And my change in VBE is just VBEQ plus VBE minus VBEQ. In other words, actually, itong baba, ito na lang yung matitira. In the denominator, ito na lang yung matitira yung VBE. Because VBEQ will cancel out with this particular VBEQ. So that is going to be the slope of this line. But what is this? Any of you recognize what that is? Can any of you tell me what that is? You learned that in math. Ano yan?
Differentiation.
Yes, exactly. No, that's the derivative. In this particular case, we will call it a partial derivative because IC is a factor of both VBE and VCE. No? Remember what I mentioned earlier. No? Sorry. No? IC is a factor of both VBE and VCE. Therefore, I'm not going to call it a derivative. I'm going to call it a partial derivative. M is actually the partial derivative of IC with respect to VBE at evaluated at VBE equal to VBEQ, or evaluated at my operating point. Okay, so if I wanted to estimate the change in IC with respect to a change in VBE, okay, so this is for small changes in, V, capital VE, no? And this is assuming VCE is a constant. My change in IC will be equal to this M multiplied by my change in V capital E, which is going to be V small b small e. I hope you're not getting confused by the subscripts. No? Basta't pag capital, that is the total signal. Pag small, that is the time varying signal. So this is the change in IC, the change in I capital C, as a result of VBE changing. No? So we're assuming that itong VCE hindi nagbabago, so VBE lang ang nagbabago. And ano yung magiging pagbabago ng IC dyan? It will be this M multiplied by VBE. Which is just like it's just parang interpolation lang. No? I have a point. I know the slope. I know the change. No? I have this point. I can interpolate this point, right? Because I know the change. I know the slope. I know this point. So I can interpolate the next point. Okay, we're going to define this quantity, itong M, no? The partial of IC with respect to VBE evaluated at the Q point. We're going to define this as the transconductance of the transistor. Why is it called a transconductance? Well, it's called a conductance because it's the ratio of a current to a voltage. So anong unit nito? Current over voltage? It's Siemens. The unit of your transconductance is Siemens. Now, why do you call it a transconductance? Okay, because the voltage is not in the same circuit as the current. The voltage is not in the same circuit as the current. So when the voltage is not in the same circuit as the current, then it's a transconductance. In other words, it is caused by a, most likely it is caused by a current control, a voltage controlled current source. No? Na yung voltage will be outside of the circuit of the current. And therefore, now using this new term that we learned, for small changes in VBE, the change in IC will just be equal to your transconductance GM multiplied by V small b small e. Okay, so what is the next thing that we have to do? The next thing we have to do is we try to evaluate this. Ano yung magiging value ng GM? No? We can determine GM from the BJT large signal model. Okay, so babalik na naman ako dito. Sorry. I'm going to go back to this. No? This is the BJT large signal model. What I'm going to do is I'm going to neglect the early effect. So tatanggalin ko muna to. And then I'm going to assume that V capital B capital E is a normal value of VBE. This is a normal value of VBE, and it should be a normal value of VBE, assuming that our transistor is biased properly. Kasi kung properly biased yung transistor natin, then our base to emitter junction should be conducting, and therefore VBE should be a normal value. In which case, itong -1 magiging negligible. No? So, doing that, okay, sorry about all of this. No? Oops. Lumabas ako, sorry. Okay. Okay, so I want to evaluate this. Ang matitirang equation ko is this. So this is assuming or neglecting early effect and assuming VBE has a normal value. So ito yung matitira. How do I get the partial of this with respect to VBE? So the partial of, so what I want to do, no? I want to get the partial of this with respect to VBE. Okay. So that's this. That's this. Okay. I'm just getting the partial of this with respect to VBE. What is the derivative of course, the IS? Pwede nating ilabas. No? Lalabas natin yung IS. So it's going to be IS, the partial of e to the VBE over dt with respect to VBE. What is the derivative of the exponential function? It's also the exponential function. Okay. However, because you have VBE over V of t, then you have to multiply the exponential function by 1 over V of t. In other words, you have to get the derivative of the exponent. So the derivative of this is I of s over V of t e to the VBE over V of t, which is what I wrote here. So this is just I'm sure you can do this. This is just a review of what you learned in your calculus. And we have to evaluate that at the quiescent point. Now, if this VBE is VBEQ, no, itong VBE na to, if that is equal to VBEQ, then notice that this numerator will just be equal to your quiescent current. No, this will just be equal to ICQ. Right? That's IS e to the VBEQ over V of t. Ito lang yan, ano? That is just equal to ICQ. So finally, I get this. My transconductance is ICQ over V of t. So the formula for my transconductance is ICQ over V of t. If I want to determine the change in collector current due to a change in base emitter voltage, I just have to multiply the change in the base emitter voltage by my transconductance, or I multiply the change in base emitter voltage by ICQ over V of t, and that will give me the change in collector current. Are there any questions? So that's an intuitive way of introducing to you transconductance. Again, it's not quite as robust as if I had done it using a Taylor series expansion, but at least you get the feel, no? You get the feel for why it is valid. Any questions? Okay, now remember that my collector current is not just dependent on my base to emitter voltage. It's also dependent on my collector to emitter voltage. That's dictated by this. Kung nagbabago yung VCE ko, magbabago din yung IC ko. In fact, this is due to what is called the early effect. No? You remember yung early effect na yung transistor curve hindi talaga flat, pero may konting slope. A konting slope in the forward active region. So how do we take changes in VCE into consideration? Well, we just do exactly the same thing we did. We follow the same procedure. So following the same principle, for small changes in VCE, my change in collector current will be the partial of IC with respect to VCE. This is evaluated at my Q point multiplied by my change in VCE. So exactly the same principle. Ang binago na lang natin is what slope we get. So the slope that we're getting now is the slope of IC with respect to VCE. Okay, the slope of IC with respect to VCE, and then we multiply that by VCE. So ang curve na ginagamit natin to determine this is actually your common emitter collector collector characteristic curves. Yun yung curve na gagamitin natin dito. These are your you call it also sometimes your output characteristic curves, no? IC versus VCE, yung mga curves na ganito. Okay, of course we have to assume that we're operating in the forward active region, so you have a certain value of VCEQ and ICQ. Okay. And this is going to be IBQ. That is the base current corresponding to your quiescent point. Okay. So you're going to have a slope here. This is the partial of IC with respect to VCE evaluated at VCEQ. We're assuming that for small changes in VCE, okay, this curve is going to be approximately a straight line, which actually it looks very much like a straight line. And therefore, we just need to know the slope at this point, multiply it by the change in VCE, and we're going to get the corresponding change in IC. Okay, we now define output conductance as the change in my output current with respect to my output voltage. Okay. IC over VCE, output current over output voltage. Again, evaluated at my Q point. So the unit for this is again going to be Siemens because it is current over voltage. So let me evaluate this. So this is again just an exercise in getting derivatives. So I differentiate this expression with respect to VCE. Notice that if I differentiate this expression with respect to VCE, then this thing is a constant. Okay. This thing is a constant. And therefore I can bring it out of the differentiation. Because we're assuming that VB is a constant when we get the partial with respect to VCE. And then I just now have to get the derivative of this term. No? But the derivative of 1 is equal to 0. The derivative of VCE over V sub A is just 1 over V sub A. So what am I left with? I'm just left with this. Okay, by the way, I have to evaluate that at VCE equal to VCEQ. At VCE equal to VCEQ, VBE will be equal to VBEQ. And that's why I have VBEQ here. That's why I have VBEQ here. Because at VCE equal to VCEQ, this VBE here will be equal to VBEQ. So, ito yung matitira. And if you take a look at this numerator, if we neglect early effect, this numerator is really just ICQ. That is just ICQ. And therefore, my output conductance is just ICQ over B sub A. Any questions? Okay. So, this is my output conductance now. And if I want to determine my change in IC with respect to change in VCE, I just multiply that now by my output conductance. Now, we define the output resistance as 1 over the output conductance. Okay. Resistance is the reciprocal of the conductance. So we can actually, instead of using G sub O, we can use R sub O. Okay. So this is going to be the expression, ano? I sub C is just VCE over R sub O. Instead of VCE times G sub O, VCE over R sub O. And you get the same, expression. Any questions? Any questions? Okay, so we've completely characterized now the output. The output with respect to a change in the input voltage or the output voltage. Now let's consider the input. Let's model the common emitter amplifier input. Okay, when you connect the transistor to a source, naturally what that source will see would be a load. What is the load that source will see? No? In other words, if I have a source, kinabit ko ngayon yung transistor ko. So let's say this is my transistor. Mangyari, pag kinabit ko yung transistor ko sa source, magkakaroon ng current dito. No? There's going to be a current, an input current that will flow. And that input current will depend on the resistance that this particular source will see. In other words, pag kinabit ko itong transistor na to, may makikita tong resistance. You might think of it as like the Thevenin resistance with respect to the input terminals of the transistor. Now remember that the model does not have any independent sources. So it will just be active elements and dependent sources. Okay. The reciprocal, well, the input resistance, we're going to call that R sub pi. We're going to call that R sub pi. The reason why we use pi is because eventually you're going to find out that the model that we are applying is the hybrid pi model. That's why your parameters are you're going to see pi in the parameters. Okay, so the input resistance R sub pi is the reciprocal of this, no? The partial of IB with respect to VBE. 1 over R sub pi is equal to the partial of IB with respect to VBE. The rate in change in input current with respect to input voltage. And we evaluate that again, at our quiescent point. Now, since IB in the forward active region is equal to IC over beta, okay, 1 over R sub pi is just now 1 over beta, the partial of IC with respect to VBE. So we're just replacing itong IB, we're just replacing this with IC over beta. So ito yung IC natin, ito ngayon yung beta. But what did we say was this? Okay. Itong quantity nito, the partial of IC with respect to VBE at the quiescent point is just our transconductance. This one, this is just equal to GM. So finally, 1 over R pi is just G sub M over beta, or R pi is just beta over G sub M. Yun ang makikitang resistance dito. That's going to be R pi. That is the resistance that your signal connected at the input is going to see. So we now have the complete picture. If there are both changes in VBE and VCE, again, these are large signal quantities, but the changes are going to be these small signal quantities, then the total change, I sub C, will be GM VBE plus GO VCE. That is the total change in your collector current. And then the equation relating the input voltage and the input current will be VBE is equal to R pi times IB. The input voltage is just your input current multiplied by R pi. Okay. So these are the two equations now that I should have written this another way, no? I should have written this as I sub B is equal to VBE over R pi. Because by doing so, then nakita nyo, these are the dependent variables, I sub C and I sub B, these are your dependent variables. And then itong VBE, VCE are your independent variables. Here we only have VBE, remember, because we are using a unilateral model. So this is now according to what we said would be the independent and dependent variables. And then you just have these parameters. G sub M is equal to ICQ over VT, G sub O is ICQ over VA, R pi is beta over GM. What will our model look like? Ano magiging itsura ng model natin? So let's try to construct our model. Okay, if you take a look at this looks like a nodal equation, no? You have the sum of two currents, no? You have your collector current being the sum of two currents. Okay, this is from a voltage controlled current source. Okay, and this is from a resistance. So if this is my collector terminal, okay, let's say this is my collector. This is my collector. I have two currents. Okay, two currents. One from a resistor. Okay, so this is from a resistor. So this is now my VCE. Remember, this is a small signal model, so this should be small c, small e. This is going to be my I, small c. And this resistance is just 1 over G sub O. Or R sub O. No? R sub O, or 1 over G sub O. Okay. Now, what about this current? Itong current na ito, that is this. So what is this? This is a voltage-controlled current source. So the direction is downward. It's a voltage-controlled current source where the value is G sub M VBE. So yun yung I sub C ko. No? Again, note, no? I sub C is composed of this current, which is VCE over G sub O, and this current, which is GM VBE. Which is VCE times G sub O, no? The resistance is 1 over G sub O, VCE over 1 over G sub O, or VCE times G sub O. And then this is GM VBE. And then let's take a look at the input. What is my input? So my input is my base. What my input will see is a resistance equal to R pi. So what I have here is VBE. Now, by the way, this is my emitter. And this is also my emitter. So my emitter is a common terminal. So this is now my model. That is my model. This is IB. Notice all linear components, in fact, all resistances and linear controlled sources. There's not a single nonlinear component here. And you already learned how to deal with things like this in EEE 123. If you have a circuit containing something like this, CCO dapat yan for you to be able to compute for whatever voltages and currents you need to know. Okay. So again, I repeated the model here. This is your NB-NBJT common emitter small signal model. I will emphasize that this is a model at low frequencies. The reason why we say it's at low frequencies is there are elements in the model which you will only learn during frequency analysis, that are not included here. There are capacitances that are not included here. For example, there's a capacitance associated with your base emitter junction, and there's also a capacitance associated with your base collector junction. And at high frequencies, those capacitors tend to be short circuits. So they will affect the performance of your circuit. At low frequencies, those capacitors are open circuit, and therefore they can be neglected. Okay, so this is a linear model. It is much easier to use than the large signal model, definitely. You don't have to do any iteration. You can use mesh analysis or nodal analysis. You can use superposition. You can use what have you, all the techniques that you already know. Okay, this fully describes the response of the BJT to small signal variations around the quiescent point. Okay, warning, it can only be used for time varying or the AC component of the input. And remember that all of these parameters, R pi, GM, and RO is 1 over GO, are dependent on the Q point. So you have to know what your operating point is for you to compute for all of these parameters. And then the other thing that you must remember is this is a unilateral model. If you notice, yung input ko is not affected by the output. This I sub B is only dictated by VBE. Right? I sub B is only dictated by VBE. Walang kahit na anong mangyari dito sa output circuit, hindi magbabago tong I sub B na to for a particular value of VBE. So that's why it's a unilateral model. Any questions? Any questions? Okay, what about the PNP transistor? What will the model of the PNP transistor look like? No, I've been remiss in discussing the PNP transistor to you in the previous synchronous sessions, so I thought it best for me to do this now. No? Okay, so for a PNP transistor, okay, you have very similar equations. You have GM. This is equal to the partial of I of C. However, instead of being with respect to VBE, it's going to be with respect to VEB. That's going to be with respect to VEB. No? Where I sub C is I sub S e to the V EB over V sub T. You remember, no? Pag PNP transistor, nagbabaliktad yung mga subscripts natin, no? And then the directions of current will also become opposite that of the NPN transistor. Okay, if I try to evaluate, sorry, no, I should have used a small I of C, no? Para consistent dito. Okay, so if I try to evaluate partial of IC with respect to VEB, I'm actually going to get the same formula for GM. So this is going to be ICQ over V sub T. It's the same formula that I'm going to get. Yung G sub O ko, this is my output conductance. This is going to be partial of IC with respect to, instead of with respect to VCE, it's with respect to VCE. VEC, sorry. With respect to VEC. And if I try to compute that, I'm also going to get the same formula. I'm going to get ICQ over VA. No? And finally, I'm going to get R pi, the R pi that I will compute, which is 1 over my partial of IB with respect to VBE. Okay. 1 over the partial of IB with respect to VBE. I'm also going to get beta over GM. So my equations for GM, GO, R pi are going to be exactly the same. Okay. Now let me draw my model. What is my model going to look like? Drawing natin yung model. Okay. So you remember that what is your circuit going to look like? Ang circuit natin, well, this is going to be your circuit, ano? Yeah. This is going to be your circuit. Here you're going to have this is going to be VEB, and then your IB is in this direction. Okay, and then here you're going to have VEC, and then the direction of IC is this way. No? This is going to be IC. Right? That is your circuit for the PNP. Okay. So my common terminal is still my emitter. So I'll draw that on top. That's my common terminal. Between my emitter and my collector, so this is my emitter. No? This is my emitter. Between my emitter and my, let's say this is my collector, I still have GO. So what is this? This is VEC. And then I have a current, okay, flowing opposite, no? Flowing down rather, current flowing down here. Okay, so nag-add siya sa current dito. This current is flowing down, this current is also flowing down. Okay, this is GMVEB. And then between my emitter and my base, I'll have R pi. So this is my base. And then this is now VEB. Well, let me redraw this. If I flip ko lang, no? Let me just flip this. Okay, so if I put my emitter down, So ito yung emitter ko. I draw my base. This is R pi. Okay. Ito magiging, saan yung plus ko? Plus, minus, that is plus minus VEB. Right? Kasi yung plus ko nasa E, yung minus ko nasa B. So this is plus minus VEB. Now, what if I just shift the ito, no? Okay? Yung EB gawin kong BE. Okay, yung subscripts i-shift ko. If I shift the subscripts, then instead of minus plus, this will become plus minus. No? So let me do that. Okay, instead of minus plus VEB, I can write this as plus minus VBE. Okay. And then dito naman sa emitter sa output side, okay. So this is my collector. I'm going to have GO. And then my current source is going to be going upward. So this is GM VEB, GM VEB. If I express this in terms of VBE, babaliktarin ko lang yung direction nito. So let me do that, no? So I will express this in terms of VBE, and then I will change the direction of this. So let me do that. So ito gagawin kong GM VBE, and then now this will be in the downward direction. And then again, this is plus minus VEC. So instead of saying plus minus minus plus VEC, I will just say plus minus VCE. Now, what did you notice? Okay. Finally, my model looks like this, no? R pi plus minus VBE. This is GM VBE. This is G sub O. This is VCE. What did you notice? Exactly the same. The model for the PNP and the model for the NPN are exactly the same. So you only have to remember one model for both the PNP and the NPN. The DC computations for the PNP would be different. You're going to have to take into consideration the reverse subscripts. But when you apply the small signal model of the PNP transistor, it's going to be exactly the same as the NPN transistor. Yes, no, sorry, that's right. Since I'm representing this by a resistor, this will be 1 over G sub O. Okay. I should really use R sub O para walang confusion. R sub O is 1 over G sub O. Any other questions? So that's it. That is my way of teaching you the small signal model of a transistor. Again, this is sometimes confusing to the students. This represents only the transistor. Transistor lang yan. No? When you connect resistances to the transistor, mag-iiba nito. This will change. As soon as you connect anything to the transistor, that will change. But at least you have a baseline. Ito yung baseline nyo. And in subsequent analysis of transistor amplifier circuits, this is what we're going to be using, this particular model. We call this the hybrid pi model. Any questions? Okay, so just a reminder. So next week, the session is not going to be over Zoom. Well, it will still be over Zoom. I'm going to provide the new Zoom details for those of you that cannot attend the face-to-face. The Zoom is going to be hosted by the EEI Institute. I'm not going to host the Zoom session. I'm going to announce what the link is going to be. I hope to see you in the Institute next week. Okay, so if there are no questions, then I will leave when the last person leaves. Thank you.
Thank you,
Thank you, sir.
Okay.
Yes, sir.